So let's, to summarize here, the advantages of the randomized complete block design is that we remove variation from the error sum of squares, making the error sum of squares smaller. Overall, the non-treatment error, that is the sum of the true error and the block error, are going to be the same. The difference is that in the randomized complete block design, we partition the error into sources that we know, that is between the blocks, and sources that are not known. This is the true experimental error. So I've touched on this, is that a practical benefit or advantage is that blocks can be used to address variation in sampling or application of the treatment. Maybe treatment, it takes more than 1 day to apply the treatments. We might apply all of the treatments for block 1 on 1 day, all of the treatments for block 2 on the next day, for example. So our experimental protocols might be time consuming. And variation in the application of our treatment may affect our plant response. If we had a fertilizer study, if fertilization was delayed by rainfall, for example, if we had applied our fertilizer treatments in strict block order, if it happened to rain before we could finish block 3, we could come back, reapply that the next day, and that would give us some protection against error that might result from variability in the application of those treatments. I already discussed operator bias between field condition technicians, and when we have the luxury of having more than one person, individuals should sample separately for each block. Another benefit is our replicates do not have to be physically in the same location. If we had a large study in the greenhouse, we could go ahead, put blocks 1 through 3 in one chamber in the greenhouse. Reps 4 through 6 could be in a different chamber in the greenhouse, or could be conducted at a different time. So we can have replicates separated in time or in space. We do have disadvantages. Primarily, if the experiment is uniform, we do have very uniform experimental material. The randomized complete block design will be less efficient because we will have fewer degrees of freedom, and because our mean square in the ANOVA table is calculated as the sum of squares divided by the degrees of freedom. Cases when we reduce the error degrees of freedom, the resulting mean square error will be a little bit bigger because of the loss of those degrees of freedom. We do always have the option that even though we have a randomized complete block design, if we suspect that if we have a small experiment and that the number of degrees of freedom is a limitation on our study, we could go ahead and conduct it as a completely randomized design, so long as we don't have an undue effect on increasing our error degrees of freedom. An implicit assumption in the randomized complete block design is that there should not be any block by treatment interaction. If our ranking of treatments was affected by the factor that was causing the variability, our randomized complete block design would not be able to be sensitive to that. So we have to proceed with the assumption that we do not have a block by treatment interaction. Finally, a final disadvantage, if we have very large studies and we have a lot of treatments, say 100 treatments, our blocks could get quite large and we could have large within block error and it could reduce our experimental power. This is most common with plant breeders. In most agronomic studies, we tend not to have a lot of treatments, but in plant breeding studies, the treatments typically accessions or plant material. And if we have a lot of lines that we're trying to test, often in breeding studies, we would use an incomplete block design to avoid this problem of having very large blocks when we have lots of lines that we are testing. So here's a possible layout. I believe this is the example we could, if we were to look in our textbook, say table 10.2, chapter 10 on page 135, we would have, we can see a possible layout, table 10.1 on page 134. This is the layout here. We can see block 1 then comprises the 4 treatments, randomized. Block 2, the treatments are in a different order because we would re-randomize within the block. Finally, block 3, the same 4 treatments in yet a third randomization. So let's look at the ANOVA table. You will recall the ANOVA table for a CRD. And so this is what our ANOVA table would look like if we analyze the chapter 10 data by ignoring blocks. So you would recognize then we have a treatment effect with 3 degrees of freedom. We would have for the data presented in table 10.3, sum of squares of 6.6, mean square 2.2, and the variance ratio, the ratio between the mean square and the error mean square. If we analyze this as a CRD ignoring blocks, then we would have the residual, we might call this the within treatment effect. Alternatively, we might refer to this as the between replicate effect. This is the variability between one replicate and another. So for the layout we had above, we had 4 replicates, 4 treatments, 3 replicates would give us 3 minus 1, 8 degrees of freedom, and these resultant sums of squares for a total of 11 degrees of freedom for the 12 experimental units. In this case, importantly, we can see that the variance ratio is quite small, and without looking up this for the 3 and 8 degrees of freedom, my prediction would be not significant. Typically, less than 2 is not significant. Now let's look at this same experimental data, but by including the block effect. The first thing you'll notice is that we have a new line in our ANOVA table. This is the effect due to blocking. But let's go to the beginning, look at the treatment effect. The calculations and the mathematics for the treatment effect for the RCBD, whether we include blocking or we exclude the blocking effect, is going to be identical. We have t minus 1, the same degrees of freedom, the same sum of squares, and the same mean square, 2.2, because it's the sum of squares divided by the degrees of freedom. When we add in the block effect, it will be calculated as b minus 1 is 2 degrees of freedom. And you can see here that we have the sums of squares with respect to blocks, and the mean square, sum of squares divided by 2. Finally, the residual, this is a new formula. This is one that you're going to have to remember because the calculation of the degrees of freedom for a complete block design is calculated as T minus 1 times B minus 1. Previously for the CRD was T times B minus 1. When we apply these, the 4 treatments and 3 blocks, we end up with 4 minus 1 times 3 minus 1 gives us 6 degrees of freedom for the error. Likewise, the sums of squares. You'll notice that the sum of squares for blocks and residual error, if we were to add those together, this is the value here, 12.18, that we had when we ignore the effect due to blocks. Total sum of squares is the same, the treatment sum of squares is the same. The important thing, which is the essential part of this design, is that the sums of squares has been partitioned into a component due to blocks and a component due to true experimental error. The value in doing this becomes obvious then when we look at the variance ratio test, when we compare the treatment mean square to the residual mean square. Now we have a variance ratio of 5.52, and previously when we did not include blocks, our conclusion would be no significant difference. Now, because we've been able to increase the experimental precision by removing the block effect, we gain we do have a significant F ratio, and we can proceed with declaring that some of the experimental treatments will be different from each other. So we have, in this particular case, a completely different conclusion when we include blocks in our ANOVA table compared to when we have blocks. We will be doing some of these calculations in the recitation later in the week. So let's, I'll wrap this up here. We'll finish this lecture and go on to, in the next lecture, looking at some of the more detailed aspects of the RCBD if we have missing data or subsamples.